Okay, how many folks knew that there was a homework today? Raise your hand. There you go. Very good. As of Sunday. Oh, good. Yeah, because like God forbid we use this, right? Well, how did you know what you were supposed to be reading? No, you did not. Did you really?
Yeah.
Oh. I didn't realize those were actually what you were like basing your decisions on. I thought you were just like really engaged with the material.
No, it was
Okay, all right. So in fact, there are homeworks due every week. And the reason that we're doing this is because the problem solving is your opportunity to engage with the material on your own, right? Because when I just, open up my beaker of knowledge and pour it into your brain, right? I got to make sure that you close that lid, you screw it on, and then you shake it up so that it's like internalized. Otherwise, if I pour it in and then you shake it and you don't screw it, what happens to all the knowledge? It flows right out. Fluid dynamics, right? Okay. So in fact, we may or may not get through conservation laws today. I only made like 12 slides. And so we'll see whether or not we do that. But I do want to get into computational fluid dynamics really fast because it's fucking awesome. And it's a lot cooler than the math. I think the math is a lot less intuitive. And the computer part of it is not more intuitive, but being able to see the way that a tensor operates like a matrix, multi-dimensional matrix, and then internalizing that, being like, oh, this is just a matrix of derivatives in different directions. I can do derivatives. Boom, you're going to understand it. Well, you're going to feel better about it. Okay. All right, here's our fluid dynamics lobster of the day. I realize we need a mascot for this class. You better work. There we go. So this is fluid dynamics lobster. This is the flow around a stationary lobster. What's that? You can name it whatever you want. This can be your personal lobster, and you can keep a copy of it in your records. And what are the things you see on this lobster? Good. And what do the different colors mean?
It looks like there's a different gradient and pressure.
Yeah, so in fact, there's velocities here in meters per second going from 0 up to 17 of arbitrary units. Where is the flow fastest over our friend the lobster? There is some green here. Yep. So over his little claw boys, they're
some red over his back.
Yeah, there's some red over his back. So as it goes over his back, it seems to be jumping up in speed a lot. We might even see that as a concept today. So what's this thing here? What? No, sorry, this equation.
Oh.
See these letters here? What are the equations in the top right-hand corner?
The gradient of the row U.
Is it?
I don't know.
It's the continuity equation.
It is the continuity. All right. John is doing my favorite thing to do at a party. Because when someone makes a really funny joke to you, you quietly, they make it quietly to you, you repeat it loudly to the group, and everyone's like, so clever. So in fact, it is the continuity equation. What does it mean? What does this part mean?
The unsteady?
Yeah, this is an unsteady term. We know that when we see the dt's, partial t's, these are having to do with whether or not the flow is steady. And so this is talking about how the density is changing. And what is this talking about? Do you understand what you said? Okay, so anyone else? Go ahead. I don't know, but what do you think it is? Okay, what do you think it is? The flux divergence of what? Good, you're very close. The flux divergence means what?
If there's no flow, you can't change density.
So that would be if the whole thing was moot, right? If the thing's not moving, that's another one of the forms where we can just get continuity, of course, to be zero. It says no flow in, no flow out, means the density won't change, means nothing's happening. That's the most boring form of fluid dynamics because that's fluid statics. Very good. Okay. Did you have, what's your thoughts about this piece here?
Second part?
Yeah, second part.
Is that just like flow and fluid?
Okay, so we're not just thinking about the lobster here. Let's think about an Amazon package. Okay, this first term says the density is changing. And the second term says flux divergence. And so far, we don't really know what that means. Yeah. Sure that there is a flow velocity. What does it mean?
Mass flowing through the surface of our parcel.
Okay, right. So if I have an Amazon parcel, right, let's say it's a box, if flow goes out of the parcel, that will cause the density to change in that parcel. If mass goes out, the density is going to go up or down? Down. And in fact, we see that because if I were to move this to the other side, this is a 0. If I move this to the other side, that would make it a negative relationship between the two. This is the definition of the continuity equation. It says that we can't create new mass as much as we try. Okay? I keep eating stuff, I can't get the mass to disappear. Right? All right. So anything that goes in will cause you to get rounder. Right? That makes sense? Stuff that comes out causes you to get rounder. Nope. Stuff that comes out is smaller. Well, so think of yourself as eating a lot of food, right? This is the eating the food part, and this is the you getting bigger part. Does that make sense? Very intuitive. Okay, very good. All right, what about this mumbo jumbo? Any terms there you recognize? What's this mumbo jumbo? Yeah.
On the left hand side, we're using the element from the continuity equation. But it's reversed. So B dot del instead of del dot B.
Okay. You're saying that this is the same as this?
It's the reverse.
Is it? This piece here, I see a del and I see a v. But it's not del dot v, it's v dot del. And which operation happens first? Are these commutative always? Not always, right? Because they're vector identities. So you're seeing some similar parts, right? And you're thinking hopefully to yourself, when I see del dot v's, what's coming up in my mind other than fear and panic? What's that? Flux. That's exactly right. Flux is what you should see when you see divergence. A del is a flux. Okay. So in fact, here we were talking. What were these two terms meaning? The first one was, and that really means intuitively, right? Another way of saying that.
Finding out.
We talked about this in office hours today.
Repeat the question.
What does this first term intuitively mean? When I see something, a partial with respect to t, which means intuitively, what's another way of saying this in English to your cousin or your friend? Yeah.
You get fatter.
So this is saying I do get fatter because I eat more, correct? So this is saying if I don't get fatter, you would call that
Skinny.
No, if I don't get fatter, if my weight doesn't change.
Got it.
A constant, a steady term. This is a time varying, so this is an unsteady term. My weight is changing. This is the flux divergence of food and or poop, right? You see that? I am the parcel, the fluid, we're in the 60% water or something. And so this is a very good analogy, very scientific. Okay, so in fact, we see it on the bottom too. And we were talking about, okay, that divergence part looks a lot like. It looks a lot like this piece here. It's not quite that piece. We'll talk about why that is. But if I just look at the left-hand side, how would I interpret that first term? VDT, yes, definitely an acceleration. I would interpret it that way, a changing of the flow velocity. But if I wanted to talk about it intuitively, the way we just talked about poop and everything on this side.
That would read and would indicate something or eat.
Yeah, so this is a rate. Yeah. Could we call it the unsteady term of the flow? dVdt, right? And what would this then be?
The change in the volume?
That's not the volume, this is the velocity. They use really bad letters.
Oh,
so,
okay.
Sorry.
Makes sense. Acceleration.
Yeah, so
Okay,
this
we got-
piece here goes with this piece here. You may or may not have seen this before. I'm gonna write it again for clarity. Have you seen that before? What is it? Good, and what does it mean? Say that again? Yeah, yes. Yeah, there's a flux term right there, good. Total derivative here is equal to the unsteady term of F plus the advection term, where the flow is bringing some quantity and causing it to change. So on the left-hand side, we're talking about the total derivative of the velocity. How does the velocity change in space and time is only due to some stuff that looks like scary, right? Okay. So we're gonna do the right-hand side today. I know it looks very, very frightening. G, like what could that be? No. Nice, 10 points for Griffin. What's this G? Gravity, probably a body force, right? Something that's operating on the whole body. What's this thing? This one looks scary, right? Very bad. Any symbols here look memorable, standy outy? What? Del squared, okay. Yeah, there's a Laplacian there of the velocity. That's not really telling me about the physical interpretation yet, though. One little symbol in there that's going to tell us what this term means. Maybe you don't know it yet. It's okay. What does mu mean here? Viscosity. Oh, okay. We saw that before. That viscosity must do something to fluid flow. Okay. What about this last one? This one's really hard. Why does gun go boom? Pressure forces. Okay, so in fact, this will be the Navier-Stokes equation. We'll derive it in detail today. Or we'll use it in detail today. And then what's this garbage at the very bottom?
Those are the stress and strain tensors?
Correct. That is the strain tensor. Broken apart into, so is it symmetric? Let's have a look here. This back one definitely is. Is this symmetric? And I have to look really, really careful. Everyone has their telescopes in the back. Okay, that looks fine. Yeah, in fact, that is symmetric. And that is the strain tensor. So we'll have to define what the hell a strain tensor is. Okay. So who knew there's homework due today?
Yeah.
Okay, who has the homework due today? Okay. So yeah, I mentioned it in class. I guess I should have. I don't know. What should I have done?
Maybe, honestly, just an announcement over Canvas, just, hey, I choose a content schedule, please take a look at it.
Okay, but do you actually read the content schedule? Should I ever update that?
No.
Never? Okay.
I looked at it. What's it to do then?
No, you can show me after. So does everyone use to-do lists on Canvas? Raise your hand.
Yeah.
I
think it sends, yeah, it sends like automated.
What was it?
Like, if you send it out here, you're like, I didn't even hear you say that.
It wasn't moved, it's just weekly.
Someone said bi-weekly.
Bi-weekly was the first week of class, and then in the second week of class, I said, I'm gonna give you a homework every week because we have too much topic to cover.
Oh.
Yeah.
Wasn't the first one doing like it was Friday though, or the second one?
Well, the first one was taking pictures of fluid.
Okay, the second one.
Yeah, the second one was a week after that, so you had 2 weeks of content. Did you not? And then you wanted every 2 weeks. I mean, how much space do we cover in this time period? Imagine if you just sat here and listened to me for like for 4 sessions, and then 2 weeks later you had to use what you learned. You wouldn't understand it, right?
The due date in the assignment, where you tell.
Is it not in the assignment?
It wasn't this.
Yeah, it was not.
Okay, note to self, we are gonna put the due date in the assignment. That would be fun. So what's a progress report?
Good thing to fill out.
Are you supposed to fill it out? What is it used for?
It can be used for either notes or for feedback on your lectures.
Okay, Yeah.
How we're doing.
it's supposed to show me how you're doing. Right? There are some people who I have really wonderful discussions with. They ask me shit, I answer the shit. There are some people who wrote one thing once. There are some people who never wrote anything ever. That's totally okay. You can use it however you want. But it's really a tool for this third thing. What's that?
Check.
Check it. So we are going to discuss this more on Wednesday at the end of class. We'll do check-ins next week. What does that mean?
We have to schedule a time with you to meet.
Yes?
and then we can start that.
Correct. Okay. Any questions about that process? Y'all know what your grade is already? 100%? You ready? You have an argument for it? Okay, your progress report backs it up? You ready for questioning? Okay. Because I'll ask you things. When I ask you to defend your grade, we'll have a conversation about the fluid. Right? So the first one is an initial checkup. It's me touching base with you. You say to me, hey, these are the things that I do not get. 1, 2, 3, 4, 5. I'd be like, that's great. You really know what you don't know. Now, what are you doing to make sure that you understand it? And you say, well, I have this plan, and before you talk to me in 5 weeks, I'm going to have figured that stuff out. You're like, great. And then I get to talk to you. I see that happened. Wow, they're really on top of their educational experience. And then let's say you come to me and you say, I want 100. And I say, why? You say, because we're friends. And I say, huh, that's about as useless as I am. So then what happens? How do I interpret that? Well, you don't get an F, but you don't get an A, right? Okay. Is this me with more hair? Okay. I don't have glasses. That's the only difference. Thanks, Jasmine. I'm gonna remember that for our check-in next week.
Everything else is splitting it.
Everything else is splitting in the gym. So I'm trying to understand how to reach these kids. Okay. So let's talk. We're gonna talk fluidity. How's the speed in the class? Too fast, too slow? Too fast?
Honestly, it was too fast.
Yeah. Of what? I mean, what's the homework for?
Oh yeah, the book is kind of useless, explaining how to convert from Lagrangian to Eulerian, coordinates, equations.
What do you mean?
Because it just gives us like one-dimensional example, and then it's like, oh, just plug R of t into this other equation, and it's like, then this is what it reduces to. I don't know what you're doing.
So you're talking about the conversions that exist in Appendix
Like
B?
example, I think
Oh, yeah, I used that example for 3.3 when I was working on it on my own, and then like, I don't know, I guess I just followed it a bit too much to the T, and then I just ended up confusing myself. And it's like,
Yeah.
when we were working on it together, it was just like way simpler than I thought.
Yes.
that's example 3.2.
Example 3.2 is where you have a question?
I don't have a question, it's just really opaque, and then when I finally figured it out, I still got 2.3 wrong. I still got the question wrong. It's like, I have no idea, like, what's going on.
I mean, you just take a derivative, right?
No, because then you have to use the derivative to like, plug in the original equation somewhere. Then you have to get the original equation from what you're deriving for u of x.
Mm-hmm.
So it's like, yeah, so u of x is just, r of t, where, r of t is x, right? Like,
Okay.
I have no idea how that fits into problem 3.3 because, u of x became like a, a multiple of y. And then, when I tried to use the total derivative, it, ended up completely breaking.
The particle flow is supposed to look like this. Correct.
Yeah.
And K, R naught, T naught are all constant. Right?
Yeah.
Okay. And it just says find the Eulerian velocity and acceleration. What is Eulerian velocity and acceleration mean?
It's the velocity and acceleration of position rather than falling apart.
Okay, so we want to evaluate it at a specific position, right?
Yeah.
Okay, so to do that, we would need the Lagrangian formula in first, right? Which doesn't matter what position you're at.
Yeah.
Okay. Correct or no? All this. So here, how do I take the derivative?
With respect to t.
Right. Right, because something like u as a function of t is the d dt of r as a function of t, which is
K over 3, all of that stuff to the -2 hertz.
all of this stuff.
Yeah.
What does that look like? Yeah, it looks similar to what we started with. Yeah, it looks pretty similar to what we started with. So maybe even right here, I could rewrite this in terms of what we started with. I could do that. A over 3 is definitely not what we started with.
And then it's RT to the -2. like that whole equation. It's two.
There's 1/3 here. 2 makes it 2/3 minus this. Okay, so if, for example, you were doing this on equation 3.3, for example 3.3, right? You would just see what was similar to the original u and x, right? U, x, y, and v. And you can just look at them and you say, wait, there's a power law still that I could apply. I could divide it by itself. In the homework.
I think the right one, there's two power ones.
No, if there was a power law. Right. Here there is a power law, right? To the minus. I'm saying similarly, I see, for example, a sine and a cosine. I know that they have these fun properties where they switch with every derivative. Yeah. So in fact, I know that y must be related to u. And x must be related to v, right? Because they're sines and cosines, every time I take a derivative, they're gonna flip. And then they're gonna look like the other. And there's gonna be some stuff that I have to figure out in between. Right? So this type of problem, right, that you see here. You can also keep going, take another derivative. What's that? Minus 2. Right, you get the acceleration. Evaluate it when x equals r. Yeah.
So like it's not like they were saying, yeah, like Faulkner is that the same helpful. And it's like, yeah, we can do that. We can sort of understand the Faulkner. When we did into the problem, it's like, shit, like something. Yeah, like I saw like this derivative of class, so how to do something like that. So I'm not
Okay, but no one wins.
Might be
I just don't understand why I have 4 of them. If I get like one person, and I ask everyone when to make them. I mean, the thing is I totally understand, right? What? What is a help session?
Yeah, when are they?
I have 4 of them. They're in the syllabus. I asked everyone for input as to when they could accommodate as many people as possible. Like they're separate things. You know, the thing is that if we do this in class, and don't get me wrong, right? I have no problem doing more of this work in class. You'll just get less material, right? So like if you want to say, well, I really don't care about shocks. I really don't care about aerodynamics. That's totally fine. We could spend all of our time in class doing the homework. But I think that does you a disservice because you really have supposedly a minimum of 8 hours or 7 hours outside of this class that you're supposed to be working on this class, right? That's what a 3-unit course means. 7 hours. Yeah, it's fucking nuts. I don't know how you do it. But, right, some of that is reading the book, okay? Maybe it takes you an hour to read the book if you're hopped up on something, and maybe 2 hours if you're not. Okay, that's 5 hours to do homework. That's to engage with the material. I have 4 help sessions, right? I see like one person in there, right? And they ask me the same type of questions that you're having here. I have no problem answering those questions. Kobe, you had a very good question. I ignored it because I didn't see it on Slack. I apologize, right? But you have to repeat these questions to me. I don't mind helping you at all. But I think on an individual basis, it's easier to see than for someone to stand up here, do a problem, and for you not to participate. In fact, a lot of the ways that I like to do student help session, they force you to stand there and do the work. Because as you go through the process, you're like, oh shit, I do see how to do it. As opposed to like here, where you stop listening for a few seconds because your phone, you know, you're getting blown up. You're like right before Valentine's Day, you're getting in trouble, right? So you look at your phone and then you don't know what's happening, right? Is that fair? So we can do an example, and I'm happy to take more time. Like we don't have to finish 4, right? We have a President's Day on Monday. Just slip in the schedule. If you want to understand something about this homework, I'm happy to talk about it conceptually. I won't do a whole problem for you. Is there a question about the homework you want to talk about? Do you want me to do more examples in the text? They're boring. They suck. I hate the examples in the test. That's why I don't do them. Okay. They're horrible examples. I mean, don't get me wrong. It's a really well-written book. They're just like, derive X, Y, and Z and show that. It's like, no, I don't want to. You should be really happy the examples I'm not giving you in the homework. There are some fucked up ones. Make the volume go to 0 and show that it's irrotational. No, I don't want to. Okay. Questions? Is that a yes or no? Is that okay? Okay. Good. All right. So what is a constitutive equation for a Newtonian fluid? A lot of words. A lot of words. A lot of words. Okay, hold on. Let's write this differently. What do we? Okay. Okay, we're going to take a step back. We're going to remind ourselves of what was happening last time. So we had this little wonderful thing. Okay. Okay. This was called Cauchy's equation of motion. What do the different parts mean? This part here? Yeah, density with relation to G. We're going to call it gravity. We're not going to use a lot of EM forces here. This is our body force, right? What's this thing? Right, the total derivative of what?
Is it of that velocity something?
Yeah, exactly. So this is the total derivative of the velocity. And what did the total derivative mean?
That changes in time, plus that changes in space.
Right. And this first part was
Steady.
and this part was done. Right? So this part is saying how the velocity is changing. Everything on the left-hand side? Yeah. 125. Equation 4.2. We're just doing a recap. Okay, so this is the total change of the velocity. Okay. And we're gonna watch how it changes in time and how it changes in space. This is the result of the change in the velocity. And this is why the velocity changes. So this piece here are the body forces. That was our gravity. What is this thing? Right? Because remember, T for strain, super easy to remember. Right? Okay. We already used S for stress. I'm sorry, S for this is the sorry. You're right, this is wrong. Stress. And Sij is the strain. Oh. Just kidding. That's not confusing at all. Yeah, that's a good question. What is SII? How did I write S?
Oh, X, Y.
Yeah.
Oh, and then.
I. Okay. So this is the partial of the velocity in the direction of the flow block. And what did this mean again? Yeah. Lengthening. Right. Lengthening. What's that?
Is that also a strain force?
Yeah, this is also part of the strain. So the diagonal terms are strength, like lengthening this way, whereas these are here. Multiple directions. How much I is going into J or J is going into I, right? Okay, so that was our S. And now I have a T. Are they related? Stay tuned to find out. Yes, they are. Okay. So we showed the strain and rotation tensors, right? And in fact, we're gonna say that Tij, that stuff right there, we're gonna say that that is also symmetric. Is that okay?
What does the T stand for?
Stress. Great. How do I that? I need a good mnemonic. Okay. Strain is S and stress is T. Yeah. Stressed. I'm stressed. How about that? Does that work? I should have spent more time figuring that one out. Okay. So what we really want to think about is the relationship between stress and deformation. I'm going to get rid of this. I keep losing it. Okay, we did this problem the other day, and I thought about a fun example that we could do here. We had some questions about strain and stress and rotation.
It's probably gonna be a stupid question, but
No such thing.
have we been talking about strains, not stress so far?
So stress is, let me draw you an example really quick. I'm gonna warm everyone's brains back up. Okay, this is Y. Sorry, this is U of Y. And this is Y. Okay. And I'm gonna draw a velocity like that. So that each of these arrows here increases as I go to the right. Okay. And then I'm going to draw a box. This is my parcel. Okay. If I imagine my parcel sits there, and this is A, B, C, D, so on and so forth. What does it look like? Say 2 seconds later. Right?
Yeah,
Skirt, right?
yeah.
Okay, so skirt. All right, so this part's over here. This part's over here. Okay. Okay, so you would say here, this velocity differential is due to a stress on the flow. How could you imagine this happening? So let's imagine that you have an actual object. Okay, let's say it has a floor. Like this is a fluid, and fluid is flowing from left to right. And at the top, maybe I'm pushing it, some sort of machine that's dragging the top of the water. But at the bottom, I'm not pushing it. So it's at rest. So it has to come to rest. And then the velocity increases smoothly towards that machine that's pulling. Okay. So that would be a stress that's acting through the entire fluid. I'm taking the top, applying a force to it from the outside, and it's deforming all the fluid underneath. But if I take my head and I tilt into a weird rotation, 45 degrees, then that looks like a strain along the principal axis that I've rotated into. So my initial coordinate system is like this, right? With Y. and maybe Z. And if I simply rotate it, that Y prime and Z prime look like this, then in fact, all I've done is I've increased this length, right? And this doesn't change, it's the same. I don't know if I necessarily did. This isn't a perfect example.
Yeah.
What is this trying to show? This is trying to show the relationship between stresses, rotations, and strains. That strain is a mathematical construct that we interpret, that fluids can do. That stresses are due to forces, but they're still representations of what fluids can do, right? This is not derived from first principles saying, I know every motion of every molecule, and therefore we understand how the forces work. Yeah.
So in this example, the flow has a stress in it. That's why it isn't like perfect, like all moving together.
Yeah.
And then when it hits the parcel, then it puts a strain on the parcel that makes it shift.
Well, so if you look at it in its normal coordinate system, it's a combination of both rotations and strains, right? And then if you rotate, it's just straining the parcel. Strains and stresses are related. Strains are the result, stresses are the cause.
Okay, so that makes a lot.
Oh, sorry, okay. Yeah. Yeah. So you stress the fluid, you're changing the fluid itself. Strain is remember when we were talking about the kinematics, we're talking about what the fluid does without giving any credence to what was causing it. So we saw that the fluids can be strained. We saw that a parcel can deform, right? We saw that it can rotate. We saw that it can expand. These are all things that the parcel can do. But what causes it to do that is the stress. So how do we take a parcel and change its shape? Now we're talking about how we do it, which is through outside forces. So we notice there that you have body forces. Body forces don't necessarily change the flow. Because if, for example, let's say this, that is filled with water. This is filled with water. If I drop it, okay, and we imagine this, okay, good. See this Instagram box? Okay, let's imagine that that's our parcel. If I drop the flow, and the whole thing is moving under gravity, does the fluid parcel deform? No. Right? It can't deform. Because the whole parcel is moving together under a body force. Here. But if I go like this and I start to spin it, right? And I start to act the walls of the fluid on the fluid inside, that is now going to translate along the fluid and deform the parcel. So if you take a fluid, and I don't recommend you doing this with the computers, if you spin a fluid, what will happen to the free surface at the top? Yeah, so we rotate the fluid, does it stay flat?
No,
No, it doesn't.
when the edit.
Right about it. What's that? Okay, hold on. Let me show the picture.
Make sure that.
Okay, here's our cup. Okay, at rest. I'm gonna spin it. Okay, now what does the free surface look like?
Like a curve?
Okay, anyone think it's not curved? Which way is the curvature? Up or down? Down.
Yeah,
Like this?
also it's concrete.
Like that? Or like this?
Oh, yeah.
Ain't no way.
Well, there is a way.
Sounds like surface tension.
There is a way. I'll show you this next week. I'll show you on Wednesday. It's gonna literally blow your mind.
Isn't it like bounce up?
Nope. Okay. So why does it do this?
Is it the viscosity of the liquid distributing the velocity.
Yeah, so this thing has a curved surface. The walls are dragging the fluid, right? And because this is in solid body rotation, the velocity here is 0. And the velocity out here is
Greater than 0.
omega times r. Yeah, greater than 0. Very good.
Right.
So in fact, that's correct. So in fact, the velocity gradient looks like that, goes up, right? And you would have a shear in the fluid, right? You would have a stress on the outside of the fluid, causing the parcels to deform. That makes sense? And in fact, what ends up happening is you have a new,
So there has to be a stress in order for there to be a strain on the parcel of fluid.
usually, yeah. I think you can do it with pressure too, but
Can there be a strain without a stress?
well, it depends on how we want to talk about pressure. Right now we're talking about stresses as like shear forces. And really you should talk about stresses as including pressure forces, which we'll talk about in a few seconds. But essentially, to deform any parcel, you have to stress it. I've shown you here a stress that's a shear stress, but not all stresses are shear stresses. Some of them can be compressional stresses, which of course, if you compressionally stress something, of course, it's going to be strained in that direction. So maybe that's not such a helpful explanation. Did I lose everyone?
The compressive strains are the diagonals in the.
Yes.
Okay.
Yes, exactly right. Yeah, so right there, right? So like the compressive strains, SII, is the diagonal pressure forces, right?
The others are shears.
The others are shears, yeah. And it's kind of like, I say it's simple, but it's not simple, right? But what it means is, how do I smush, right? I can either smush the box like this, or I can smush the box like that. And that's about it. And then I just have the other directions to look at. Does that make sense? Because if you make your box small enough, over a small distance, you can only do two things. If you make a big box, for example, you could like bend in the middle. That's not very helpful. Make sense? Good? Okay. This example here, I love it. It's a paradox. It's one of my, I should do it right now, but I'm not gonna do it. Okay. Do it. We don't even want to work. Okay. Okay, so T is the symmetric stress tensor. T, stressed. I'm stressed about work. And you could do this with any fluid flow. So I'm in prepping for this class, I did it last night in my notes app. I just made an arbitrary velocity curve, and then I like deformed the fluid. And it's not always the case that you can simply rotate into a principal component and see the lengthening, right? Sometimes the stresses are more arbitrary. So give me an arbitrary fluid flow with respect to Y.
Right.
Show me an arm motion that is an arbitrary fluid flow. Okay, I saw something like this. Is that okay? Yeah. Okay, so then you can just connect them. And here's my box. Now I challenge you to do what I did in bed last night, which is to draw what happens next. And the winner gets a dark chocolate salted caramel bar.
Yo, the stakes are high.
Bro, I should have been paying attention.
So
I don't think that A and B should remain parallel. Yeah. Are they not? Let me see. It's hard for me to see.
Wait, do you mean A, B, and DC or A, B, and DC?
Yeah, A and B are like that, right?
Yeah.
Yeah. Are they straight there?
Yeah.
Nice. Ready? Oh, sorry, I was in a good throw. No. Don't look at his screen like that.
Oh, it's small, I will admit. Probably not.
Okay, it's close.
That was wrong.
You're on the right path.
Yeah. I'm thinking.
Think about where the velocity is. So.
How? This is that. How?
Okay, does anyone want to draw on the board what their solution was?
Even if it's wrong.
We want to understand the strains and stresses in this fluid. And we were able there to just rotate into a principal axis that allowed our strains to be diagonalized and along just SII, right? So if I rotated my head, this was SYY, expansion and Y, right? Do we think we can do that here? Look at the picture you have. Solid. Fluid. What do you got?
Things like that after.
It stays like that?
Yeah.
You think it's a trick question?
Yeah.
No, it's not a trick question. In fact, what happens to this front wall? Yeah. It gets pushed in. So all of these parts move more than all of these parts.
The top and bottom.
Believe in the top and bottom. You might as well, you don't even have to care about them. So let's go like that. A, B, B, C. Okay, this thing becomes bowed. And then the other side, of course, has to become bowed. Okay, and now what happens? The inside is it's fucked, right? Well, no, not exactly. Can just do that. That. And then it's symmetric. Really good job drawing, Mateo. What an artiste. I don't know if it's correct. I don't know if it's correct. This is an approximation. Now, if I look at the two of those, can I rotate from one to the other? And so it's just compression along the axes. No, that's absolutely correct. So that first example was chosen on purpose to demonstrate a point. But in general, fluids are much more complex. Here we have deformation in both X and Y, right? And there is no like principal diagonalizing direction. I don't think there is. There might be, I don't think so. Okay, does that make sense? So weird stress causes really weird strains, non-diagonal type strains. Okay. Yeah, that's like a nub of a nub. Yeah.
So this is just in the S and I direction then?
This is in the what?
Just the I direction. SII.
That was I direction, but only when you rotated into the principal component.
For what's this?
That one is multiple. That's IJ, JI, II. Right? What? Where's
It's not a simple, it's not simple.
yeah, it's not simple anymore. This is just an example of how complex these strains can get.
How is it in the gearing direction?
Well, I and J.
But there's nothing moving up and down, no, it's just being pushed.
Yeah, but remember that IJ is the stress from I into J, and it's symmetric. that J is also into I, right? How does the stress tensor look?
Strain. Tensor.
Or the strain tensor? Let's just imagine 2D.
The strain tensor, just the diagonal.
Strain tensor is on the diagonal, let's say like that. And this one? Is that it?
Then pseudo?
1/2. And then the derivative of.
That's the definition for sure. But let's imagine that I don't want to write that. It's like y, yeah.
Yeah.
Okay. What about this one? Yx. And what do I know about yx and xy?
Imagine.
They're symmetric, which means they're the same. So sxy must equal syx. That's not always the case in matrices, right? But by construction, this is. Now, of course, when you look at the definition, they're derivatives of one versus the other, and you just add them. So, of course, adding is commutative, and you don't have a problem here, right? So it's the off-diagonal terms that are causing this to be stupid. Okay. Okay. Now, in a static fluid, you have isotropic stresses. What are isotropic mean? Same in what? Same in all directions. So if you imagine that the fluid is static, can you have stresses? No. And where do your stresses come from then? Pressure. So I said before that we need to distance ourselves from this picture in our mind of stresses being only this shear stress. So we can have pressure stresses and shear stress. And the first part of the stress tensor is this piece here. Oh, I have no space anywhere. Okay, so the easiest part to write here is this. What's that delta ij mean?
One when they're the same.
What?
It's one when they're the same.
And it's
0.
right. The Kronecker delta, right? Right? So what does T look like so far? Negative P, where? Is that symmetric? Is that easy? Yay, right? That's just pressure. Simple. Okay, now let's make it harder. Fuck. Okay, so what is what's this other stuff? Let's add some motion in. Let's add some shear stresses. So I have this piece from before, but now I have motion. And I'm just going to add that directly with this nice guy. Oops. Who's that? Yeah, what's tau? We've seen tau before, just trying to remember where. Yeah. Well, indices are gonna take care of that for us. What did tau mean though?
Did you see it earlier in this semester? Like,
Yeah, we definitely saw it this semester. I'd be messed up if I didn't explain it to you. It's equation 1.9. So on page 9.
Newton's law of viscous.
Yeah, Newton's law of viscous friction. And there's another way to write that. Okay. So in fact, we were talking about stresses being due to so we had some stresses due to pressure and some due to shears. How can we translate a shear? That is to say, how can I communicate the fact that this is being forced from here to here if, say, the viscosity in the fluid is 0? So if I have a fluid, no viscosity, no interaction between material layers, then I could spin the outside of this and the interior wouldn't spin up. There'd be no way of transporting that force, that shear force, from the exterior inwards. And that's what viscosity does. It takes a velocity profile that starts off with a large value up here, and a small value down here, and it distributes it. Okay. So we talked about that when we talked about equation 1.9, but in fact here, it's just the gradient of the velocity. So just like when we talked about, for example, mass flux or heat flux as the gradient of the temperature. So if you had, for example, so you had a temperature profile that looked like that, and you use Fourier's law, which is heat conduction, which looks like this. Gradient of the temperature is equal to the heat flux. And you looked a few seconds later, what would that heat do? Yep. Can you do that larger for everyone? Yeah. Okay. So in fact, it would do this. Gradients love to smooth stuff out. So we keep seeing ddx, and maybe we're forgetting about what they mean, right? So I have this like advection term, but if I'm advecting the fluid itself, right, that's smoothing it out. It's getting rid of homogeneities, right? And if I add a little viscous term in there, this is the definition of viscosity doing this redistribution of the velocity. Does that make sense, or did I lose people? Okay.
Professor,
Okay. Yeah.
so are you saying that in a very viscous fluid, even if you put a shear stress on the outside, when you rotate it, it wouldn't translate to the inside of it, or the opposite when there's no viscosity?
The opposite. So an inviscid fluid, one that has no viscosity, could not translate a shear force.
Okay, yeah, that makes sense.
Yeah. Yeah. Okay, good. Okay. So in fact, we can do all sorts of fun stuff. You love matrices? Do you want the matrix math? You do? Okay. We have fun index math. Okay. I need better chalk. Here we go. Let's go. Okay. So let's call this thing tau ij. We're going to call that kijmn. And this thing smn. What's S again?
Rest.
Strain. Okay, so this is the strain tensor, and this is a really fun tensor. What does that one do? What? How many components does this tensor have?
4.
No, that has 4 axes. How many components does it have? What?
16?
Well,
It has 81. We're not gonna write them out. We're not gonna write them out. But what this allows it to do is it allows us to relate every pair of MNs to IJs. It's a 4th order tensor such that we can relate all of our little variables here that we care about. Okay. We're not gonna write it, I promise. You can write it if you want to, in terms of delta Dirac functions, or Kronecker deltas, however you want to call them. IJ, MN. I mix these up. And why you don't write things out ever. Okay. So why did I do that? Of course, we're not going to write out the actual feelings, but we're going to say what this means. So what we did here is we have something that is convolving the different directions. So here I have M and N in terms of the indices that we care about, right? And here I have I and J. And we're going to give the fluid some properties. We're going to say that the way that it shears in this direction versus the way that it shears in this direction versus the way that it compresses, right? Arbitrarily. I'm going to call that gamma, mu, and lambda, mu, and gamma. And we're going to assign those properties of the fluid. Noticing that, in fact, a lot of the fluid dynamics that we use, we just measure the properties. We said this fluid behaves like this, right? Newton's laws of viscosity are empirically derived. He didn't have quantum mechanics. So he just looked, this is how the fluid behaves, right? Okay. And so we can do that. And you can make some arguments about the fact that tau is symmetric and everything else. And you will realize that this piece here is this piece here. If you like tensors, they're the same. Right. And so the only things that actually matter are this one and this one. So I can write write it right here. Can you see that? No.
there's
Okay.
a space on what.
Okay. Tau ij is 2 mu s ij plus lambda s n delta j. Okay. What's the point of that? The only point of that is that this piece here, this and n, is del dot u. What does that mean again? What is del dot u? Divergence of the velocity, yeah. How do we interpret that?
Enough was enough flux.
That was the eating part, how much you're eating.
Yeah, another way of saying this would be the volumetric strain. Okay, because we are in fact relating it to the strains here. This is the volumetric strain. This is the gradient dotted in the direction of the velocity. Remember over there, we wrote del u del x in index notation. Look at that here and look at that there. That's the same thing.
Nice.
Correct or no? So this piece here, okay, is del dot u. We use the Kronecker delta to get rid of the off diagonal terms. So we don't want them. And we want to interpret it. Okay, so I have 2 times this thing mu, we haven't defined it yet, versus the entire strain tensor, plus some stuff that just comes from volumetric change. That make sense? Even if it's not, even if it doesn't mean anything, does it make sense? Don't see how to use it? Okay, what are you missing?
I got lost starting with the definition of MN.
Yeah, so MN here is del dot U, it's something that I just chose. Because I looked over there and I said, hey, I know that the strain tensor has these fun properties. I know that the diagonal is the volumetric strain, right? So this is the definition of MN, the volumetric strain rainbow, just along the diagonal. Okay. Okay. What's that?
That's the stress. That whole thing.
This is the stress tensor.
Yeah.
Which is pressure plus this thing.
Okay.
This thing here was this thing that I chose, which is how does it stress in every direction? It stresses in this direction, it stresses in that direction, and it stresses in that direction. But because it's a symmetric tensor, we could collapse these two, add them up together, and we got 2 of them. Plus the one that was only in the direction of the principal component, the volumetric stress. That make sense? So these would be shears, and these would be your volumetric stresses. And then we,
Stresses or volumetric?
sorry, volumetric strains that are causing the stress. And then we can just put this piece here back into here. I say just, but you know what I mean, right? Okay. So we can write this, where do I want to write it? This one's gone. Sorry, folks. Okay. Oops. Right? Super easy. Right? Totally intuitive. Makes perfect sense, right? No. No, of course not. This is absolutely not intuitive at all. That's totally okay. But this is what it means. This is the generalized stress tensor. I have pressure terms, and then I have these weird terms here. Don't make a lot of sense because we haven't defined what this is or what that really is. Right? So if you have no volumetric change, okay, what's another way of saying that? Can't compress it. Right, so I could drop these terms off. Okay, and I would understand that these pieces here, the stresses are due to the pressure on the outside in the direction of my box versus the shear, right? This part here, compression, compressional stress, right? Okay. We can define some dumb stuff, which is called the coefficient of bulk viscosity. Okay, and I don't really know if I want to write it again, but you can look at equation 4.36, which compares this idea of bulk viscosity. To first order, when we think about the viscosity of a fluid, you would say, well, the way that the molecules interact with one another should be uniform in all directions. right? So that U, that mu and lambda, they're the same, more or less. Whereas that may not be the case. Fluids might be more resistive to shears than they are to compressions. What's an example of that?
Did you say more resistant to shear than compression?
Mhm.
So you can't spin it as well as you can shrink it.
Sorry, so you can't
So you can't
spin it
spin it
as well as you can smush it.
Yeah.
Or vice versa. You can smush it easier than you can, wait, you can shear it, you can shear it more than you can smush it. All right, we'll give some examples of that later.
But that's
Um,
like this water, right?
What?
That's like this water, right?
Water is easier to move than to press, right?
Yeah.
Yeah, that's a good example. Any other ones?
I mean,
All right, we don't have enough time, sorry. Okay, Stokes' assumption, which is my favorite part about old math. Yeah, he just said that if you write the definition of the bulk viscosity, which is mu nu is lambda plus 2 mu over 3. Okay. So that's the coefficient of bulk velocity. Sometimes you'll see mu, that's a version of viscosity. Oh my god. Okay, or sometimes you'll see bulk viscosity, and Stoke was like, I bet that's 0. So Stokes' assumption says that is 0 to first order. And that's a pretty good assumption. Okay, so the point of this is not to get you really upset, to write all that stuff out and then immediately say that it's 0. But essentially, you can write this all out, and 4.36, the one that I didn't want to write, but is sort of related to this 4.3. Oh, fuck, we're so over time. God damn it. Okay, I have to let you go. We'll talk about this. This is how you interpret these non-Newtonian forces, and you see that the relationship between the stresses and the shear forces are proportional. So this is relating what happens to the fluid versus what I did to the fluid. This is supposed to be like the crescendo of stresses and strains that you see that they're related. But I ran out of time. Okay, questions? Maybe.
Yeah, no, I was just, I know.
Okay, I think there's 2 tomorrow.
I think so. I think there is.
Yeah.
That's
There, you can also come to the Astra one. You just show up and I help whoever's there. Yeah, so the next one is actually not, I think it's at 1. Yeah. Sorry. Oh, thank you. How'd it go?
Okay.
Hated it?
I think it was number 3, the street one.
Mhm.
That I have trouble with.
Okay.
And also, the diagonalizing, I think it was, stress